Before the workshop, I have asked you to learn some pre-courses. So we have 3 courses online. So the first one is the Introduction to Relational fMRI, the principles, the methodology, the applications, and also the second part is the applications. The third part is REST Meta MDD, which is we just for the international conference, and we introduced REST Meta MDD. So from the pre-courses, we have learned the basic principles for relational fMRI. So if you didn't learn that, maybe some part from this part, this is almost the fourth part of the course, you will not understand. If you didn't understand, you just go back to watch the first 3 courses. You just try to understand the concept there. And this part, we are going to introduce DPARSFA. So mainly, this course is both for DPARSFA and the DPARB itself, and all are integrated in DPARB. But we would like to introduce DPARSFA first because DPARB itself, all the operations are pretty similar like DPARSFA. If you can use DPARSFA, then you can go to very smoothly to use DPARB itself. So DPARSFA, long time ago, back to 2009 actually, I started to develop DPARSFA, and in 2010 we had a paper, and this paper has already settled for more than 1,800 times. So 1,800 times, that means 1,800 work has been used DPARSFA to process the data and publish papers. And basically this is the main graphical user interface of DPARSFA, and you can download at alphamart.org, and now we integrate it into DPARB, and is freely available online. It's open source, so you can just even you can read the source code, you can further develop for the other tools, and these are programmers. And so basically we have lots of operations in data analysis. But basically we follow the logic that we have the data. So first we do pre-processing, and we have all the measures. And after calculating the measures, we can perform the statistical analysis. And for statistical analysis, we also have the concept there of, for example, we need to do sample t-test, or correlation analysis, or ANOVA, and afterwards we need to perform multiple comparison corrections, which is a very critical question nowadays. And finally, we will do the results viewing. We will view our results and see where are the significant results. And based on significant results, we build some table and make some pictures, and finally write a paper. So basically, this almost 2 days course, we will go over from the beginning, how to pre-process data, and how to calculate the measures. Actually, the meaning of the measures, you need to go back to the first 3 courses. You go over, understand what measures means, and we will go over all the statistical analysis issues and how to view our results. And the first part is DPARSFA. All the pre-processing is in volume space, and the second part is DPARB itself. All the pre-processing is in the surface based. So basically, what we are going to do in the pre-processing, basically we will first do some stress timing, and then do real line, and do nuisance regression to remove the noise signals, and do a spatial normalization, do smooth and calculate ARFF, and filter the causes. Usually we cannot filter before ARFF and FF because FFF is a low frequency band amplitude normalized by the full frequency amplitude. So if you filter first, then you lost the full frequency band information. So we need to do filter after ARFF and FF calculation. And afterwards, we can do the functional connectivity. We can calculate regional homogeneity. We can calculate degree centrality, or Vox or mirror homotopic connectivity, etc. And this is the order that we calculate the measures in fMRI space. There's also an alternative order. We can calculate all the data in original space. So we can do the source timing, perform real line, perform nuisance regression, and before spatial normalization in the original space, we can calculate A of FF and do filter and calculate functional connectivity, regional homogeneity degree, etc. And at the end, we do spatial normalization and perform smooth. And up to now, I haven't seen a paper yet to discuss if calculating original space is better or calculating hello. So or calculate in the fMRI space is better. But if you're interested, you can just perform such an analysis to see which is better. And in DPARS, we have some template parameters. So you can use template parameters. So either you would like to calculate in fMRI space, or you would like to calculate in original space. If you select template, then all the parameters was set up for you. So you just follow that streamline. If you do not understand the details, so basically you can just use the default. So the default parameters is some we think is up to date, and it is follow the current standard, and you can use the default parameters. What you need to do is firstly you need to organize your data. So once you got the data from the scanner, you organize it into certain format, and after you organize it into this kind of format, then what you need to do is just single click, just click run in DPARS, and you can get all the measures, and we can then later perform the statistical analysis. So what we have to do is we need to organize our data like fun raw or T1 raw. Fun raw is the functional raw data, and T1 raw is the structural raw data. So in the fun raw is functional raw data, you have several subjects, and the T1 raw is also the structural diagram data, you have several subjects. And if you do not know how to organize that, you can go to alpha.org/demo data. You download the demonstrational data. So in the demonstrational data, you can have the data structure. Actually, most people, if they have an error in running DPARS or DPARS itself, the most common errors you didn't organize the data well. So for example, in fun raw, you have 4 subjects, and in T1 raw, you only have 3. That would be a problem. Or in fun raw, you have sub dash 001, but in T1 raw, it's sub, there's no dash 001. The 2 names are different. That will be a problem. And also, probably, this is sub 001, and this is sub 001, and at the end, you have a space. And you cannot view that, but the space will make the 2 names different. So usually, this is the most common errors in using DPARS. So we are asking you to very carefully to organize your data. Once you organize your data, then the running will be very smoothly. And also, we also accept not raw data. For example, if you download from the internet, there is a lot of open data. So for the open data, you can, what they have is not diagram data, but they have .ni, .gz, or .ni, or .image. They are nifty data. So DPARS also can start the processing with the nifty data. So what you need to do is call it fun image and subject 01, subject 2, subject 3, and put the .ni.gz or .image into that folder. And this is also T1 image. And there's one problem is, so if you get the diagram data from the scanner, for example, GE scanner or Siemens scanner, so the data looks there's no clear structure, and it seems it's very difficult to know which data is which subjects, and which data is which is resting state, and which is structural data. So what you can do is use DPARSFA. So DPARSFA, there's utilities. So in utilities, there's a DACOM sorter. So what you need to do is click DPARSFA utilities and click DACOM sorter. You can use the DACOM sorter to sort the data. So what you will have is a DACOM sorter. And in the DACOM sorter, first you can tell it what the suffix of the file name. So for example, you got the data from Siemens scanner, then it may be it's a .ima or .dcm. So you can tell it is a IMA or DCM, or none. None is for GE scanner. For GE scanner, you just have the files and there is no suffix. So you just tell it none. If you tell it none, you should be very careful in those folders. There are only DACOM files. You should not have some, for example, text files or other files, because in that way, the software will consider all the files are DACOM files and trying to organize it. So, and once you tell the suffix, you click Add All. So you do not need to add subject by subject or just single series. What you need to do is, for example, you get the data from the scanner, you have 100 subjects and many different runs. What you need to tell DPARSFA DACOM sorter is just click the very top folder. So if you add all, tell it the very top folder, then it will search every subfolders of all the directories. And will all the files, all the DACOM files, it will search out and sort for you. And you can tell the output structure. You can put it, if it's a subject ID, so subject 1, subject 2, and then the T1 data, rest data, task data, or you can put a series name first. And you tell it where you want to put the data, and finally you can get all the sorted data into that directory. And there's one more thing is you can also anonymize DACOM files. For example, if you want to share your DACOM files with some other people, then the DACOM files are very detailed. So they have the birthday information, and they have the name, they have lots of privacy information. So if you click the anonymized DACOM files, then it will remove this kind of privacy information, so safely to transfer the DACOM data to some other people. And then you click sort, it will sort all the DACOM files for you. So from the scanner, you get this random order data, and after sort, you get all have very clear structure data. And the data preparation, what you need to do is arrange each subject's fMRI DACOM files in one directory and put them in fMRI directory under the working directory. So for example, like this. This is all the functional DACOM files for subject 1, and the subject 1 just put under fMRI, and the fMRI data put under this L analysis. So this L analysis is the working directory. So you always remember the working directory is not a fMRI directory, it's one level up. So L analysis has a subfolders called fMRI or T1 raw, so that's a working directory. So the L analysis is a working directory. Later you need to set up in DPARSFA. And similarly, so for the T1 data, for the structured data, you also need to organize the DACOM data. So for this is the subject 1's DACOM data for the structured data. So for the structured image, you put it into subject 1 and put it under T1 raw, and afterwards this T1 raw is put under the working directory. It's L analysis. So under the working directory L analysis, you have the T1 raw, and the program can search the structured data, and also have the fMRI can search the functional data. And you can call DPARSFA. So at DPARSFA, you need to set up is tell what's the working directory. So working directory, that means under the working directory you have fMRI and T1 raw is basically L analysis what we have just sorted. And what you need further to do is this, you need to do anything about the subjects list. The DPARS will search the subjects, all the subjects under a folder structure, only if you set up at the bottom right, the starting direct name. So you have to finally set up the starting direct name, then the program knows where to start to search which folder to have the subject list. So usually after finally you set up the starting direct name, it will search all the subjects. And if you have a right click, you can remove the selected participant. If say the folder is weird, have a weird name, you can just right click and remove that participant, or you can remove all the participants, or you can load participant ID from a text file, or if you like, you can save the participant ID to a text file for further usage. And here is set up the 10 points. So we know when we scan the brain, it's not just a single moment to scan all the brain. So it just scan the brain slice by slice. So maybe need 2 seconds to scan all the brain, and maybe over 8 minutes, so we can scan 240 volumes of 240 tampons. So here it tells the program how many tampons we have. Also, you can put the tampons to 0. 0 means the program will not check the number of tampons for you. If you set up 240, it will check for all the subjects if that's really 240 tampons. If you didn't set up to 0, then the program will not check that. Sometimes bad things can happen. Some subjects may missing lots of tampons. If you didn't set up that, then this error cannot be catched. And here is set up the TR. So TR is, like I said, is we scan the brain. It's not at a single moment. We scan slice by slice. When we scan the whole brain, we may need 2 seconds. Or currently, lots of multi-band sequences we can scan in maybe 600 milliseconds. But here you can set up a TR. Alternatively, you can set TR as 0. As 0 means what? Means the NIFT data, the header has the correct TR information. So basically, if you started with the DACOM data has the TR information, so you can put 0 here because we have the correct TR information. But sometimes if you get the NIFT data from other people or from some online data, sometimes the TR information in those files are incorrect, so that you need to set up the TR here. And here are the template parameters. So as we discussed that we have lots kind of different templates we can process in fMRI space or in the original space. So this is different setups, but usually we can just use the default. And this is EPI DACOM to NIFT. So basically, if you have the DACOM files from the scanner and you use DACOM sorter to sort the files and you organize it into file ROM and T1 ROM, so you do not need to manually convert the DACOM files to NIFT data. What you need to do is a single check. Just check here, EPI DACOM to NIFT. Then the program will call DSM to NI to automatically convert the DACOM data to NIFT. And here's apply mice. This is usually useful if you want to process the data again, because there's one step called manually reorient. So once we reorient this data and reorient the function data, it's very time consuming, and you do not want to do it again. If you want to start over from the very beginning, then you can apply the mice because the reorient matrices are stored in reorient mice. You just rename it to downloaded reorient mice and just apply it. But usually this function is rarely used. And here is remove first tampons. So as we know, the subject go to a scanner, they may need some time to just be familiar with the environment. Or the magnetic field needs some time to stabilize. In that case, we usually remove some initial tampons. So, for example, if we have 240 tampons, we remove the first 10 tampons. And sometimes, if you want to remove lice, usually most people will remove the first 10 seconds. So 10 seconds means 2 seconds TR, you remove first 5, or at least remove first 4 tampons. If you don't remove that, you will see the data there is a drop. So I recommend you to remove first 10 tampons or so. And this is stress timing. So why we do stress timing? We do stress timing is because, as we said, when we scan the brain, it's not just at the same time, it's slice by slice. So you can think about that. So the scanner may be just excite some slice and receive the signal, and excite the second again the slice and receive the signal. So that will be a problem. So if the two slices too close, then you excited one, and if they are not relaxed to the baseline, you excite again. So you will get some wrong signals. So then we can think about, if we have this kind of problem, we can use interleaved scanning. For example, we scan the first one, then the third one, then the fifth one, and come back to second one and the fourth one. So then the gap is much bigger, so the overlap problem is less severe. But let's think about this. If this region, for example, we scanned 15th and 17th and 19th and come back for 14th, 16th, 18th. So when you scan the data, you will see the 15th and 17th at the very beginning and the 16th at the very end. So there's a time differences. So for these time differences, we can use interpolation to interpolate the data. So, for example, since they are acquired at the same time. So this is slice timing. And for slice timing, what you need to do is you tell the program how many slices. So usually you can get the information from the DICOM data, or the technician will tell you how many slices they scanned. If you don't know, we can also later use macro or use DPIB to view the image, and that will tell you how many slices there are. If you put a number 0, that means the DPARS will assume some kind of slice order. Usually we do not recommend that. And the next thing is slice order. You need to know what is the correct slice order. So usually the technician can tell you what's the correct slice order, and basically most of the cases we acquire the data are interleaved order. So interleaved order is you have 1, 3, 5, and then back to 2, 4, for example, like that. But there is one thing you need to keep in mind. So for GE scanner and the Siemens, for GE scanner, they are always start from 1, 3, and 5. But for Siemens scanner, it depends on the total slice number. If the slice number is odd number, for example, 33, then it started from the first, third, fifth, and then second and fourth. But the total number is even number. For example, 32, then it started from the second, fourth, sixth, and then back to first, third. So that should be incautious. For example, if we have interleaved scanning, we have 33 slices. So this is the odd number. In Siemens is always first, third, fifth, and then second, fourth. So you can use some MATLAB expression to do that. So it's 1, then 2, then 33. So that means, so from 1, and then there's a gap 2 and to 33. And then from 2 and a gap 2 and 32. So it expands, it's 1, 3, 5 to 33 and 2, 4 to 32. So this is the slice order. And here is a reference slice. So reference slice is usually what we got at the middle time. So if you have 1, 3, 5 to 33 and 2, 4 to 32, then the middle is 33. So we can put 33 here. If you have the even number, so for example, P is from 2, 4, 6 to 30 to 31 and then to 32 and 1, 3 to 31. So that means at the very middle is you can use the first. And this is real line. So why we do real line? Because we always ask the subject to keep the head still, do not move the head. However, we will see the subjects will always move their heads. So there's a head motion. Head motion should be taken care of very carefully, and later we'll discuss some more about head motion control. But the first thing is real line. So the images they are not aligned, so we can realign them to remove the head motion effects. And you can check head motion. So in the working directory realign parameter, there's a subject directory. In the subject directory, there's rp-txt. This is realign parameters. It has 6 columns. So the first 3 columns are XYZ translation, and the latest 3 columns is XYZ rotation. And also you can have the FD power is framed as displacement by powers formula and Van Dyck, but most used is FD Jenkins. So this is also called relative up noise, and this is we recommended because in one of our work we found the FD Jenkins is more close to the box-wise displacement. And you can also check head motion in the realignment parameters folder. There is exclude subjects according to max head motion. So this is a very long time ago. We exclude subjects in this way. So we set up a maximum head motion, and for example, you can set up 1 millimeter and 1 degree. In that case, these kind of subjects need to be removed. But nowadays, we do not remove subjects in this way. Usually, we exclude the subjects according to mean FD. So you can open the head motion.tsv or .csv. You can just use Excel to open that file. So there's many columns have the max or mean motion or mean FD. So the last column is always mean FD Jenkins. So the last column is mean FD Jenkins, is a head motion index. So later we can use the mean FD Jenkins, the last column, to exclude subjects. And then in group analysis, we can use the mean FD as a covariate. And you can threshold subjects like, for example, use group mean. Usually we use mean FD at 0.2 millimeters to exclude subjects. But somehow, if you are doing some case study or some disease study, lots of subjects will have head motion more than 0.2 millimeter mean FD. In that case, if you set up that such a strict criteria, you will have very few subjects left. So another way is use your group mean FD and 2 SD, 2 standard deviation, and use that as a threshold. Somehow, some reviewers can accept that as well. And this can call the box-specific head motion. So we propose, but we didn't find it's very powerful. So this is just calculate box-wise head motion. If you're interested, you can do that. And this is a reorient functional. So reorient functional, and we also have the reorient T1 data. So why should we do that? This is also could improve the accuracy in quantization, segmentation, and the spatial normalization. And also, it's a very important quality control step. So for example, if you have this kind of data, the initial position is very far away from the standard position. So sometimes it can normalize good, but sometimes it can find a local minimum. If it finds a local minimum, then the normalization will be very bad. So what you need to do, you can set up the pitch, roll, yaw, and you just put some numbers, for example, 0.1 or 0.2, you can see how it affects image, and you can determine how to better reorient the pictures. And also by the end, you just click this cross to the anterior commission, because MR space take the anterior commission as the origin, so you need to click there, and after that you can set up the figure. And also here is for quality control. So because you can see these subjects' data, and in this way you can see this data if it's good or not. And then later we will introduce you some bad images, some examples. If you view this kind of data quality, you will know this data should be excluded. And you can make a note here. Make a note, make a comment. Okay, this data is bad, but why it's bad? You can make a note. And afterwards, you just click reorient images. So after reorient images, what you have done, you click, that will apply to the pictures, and your quality control commands will be saved. And this is also for functional data. You do the same thing. You just reorient, give the pitch, roll yaw parameters, and click the anterior commission. It doesn't need to be very exact, but just somehow nearby is okay. And you just quality control, give the quality control score, and give the quality control command. And this is the details. And the quality control scores is going to be stored at a working directory quality control, and later we will use that quality control scores to exclude subjects, and we will finally make a group of subjects which are suitable for the group analysis. And this is the auto mask generation. So why we do this? And the auto mask is very useful checking EPI coverage and generate group masks. So we know the data, so the functional data is not always cover the whole brain, so we can create a mask, so what boxes are covered during the scanning. So if we have these masks in the group analysis, we will know what kind of brain region has been covered in all the subjects and what are not. So we can use an auto mask to generate group mask, which somehow is important, is because if we do not use a group mask in the edge of the brain, somehow you will find significant results. For those significant results, it's not reflected true effects, just simply because some subjects are not covered. And you found that kind of differences. You cannot believe in that results. So the best to do is create an auto mask and create a group mask to solve that problem. And this is T1 DECOM to Nifty. So if your T1 data is in DECOM file, so just click this one, convert to Nifty. And this is just cut a knife, but usually we do not need to do that because DECOM to Nifty automatically do that. And this is reorient T1 we have introduced. And then this is BAT. BAT is brain extraction, is also scar street. And what here we do is for this can do better concentration. And for Linux and Mac, if you click this button, you need to install FSL. But in the most cases, you do not need to, because I think most of you will install DPARSFA. So once you install DPARSFA, so there's a DPARSFA Docker. Within the DPARSFA Docker, there's FSL. We will call that one. For Windows, you do not need to think about anything because we use a Chris Roden's compatible version, so you do not need to install anything. Everything can be done automatically. And why we do BAT? So here, you look at the structure image, you can see the skull, and in the functional data, the skull is not obvious. So if you cross the T1 data to the functional data, then the skull will be a confounding effect. So sometimes we make the concentration bad. So BAT can do that, can do the brain extraction. So you will see the skull is removed for the T1 data and for the functional data. Now when you crash this one to that one, then the confounding effects are removed. So the correlation will be better, and you crash the batted one T1 data to the functional data, and you have the matrices. You apply that to the original with the skull one, then you use that one to do segmentation. Because in SPM we have the probability map of the skull, so we use the one with the skull to do segment. So this is what we do but in DPARSFA. But in DPARSFA itself is a little different, because DPARSFA itself it's very important to have very good, to have very good bad quality, because we need to reconstruct the cortical thickness. All the cortical surface need to be constructed very well. So if the bad is not good, then that will fail. So in DPARSFA itself, we use some other algorithm to do that. So we will discuss that later. So this is in DPARSFA, we do that, we can do better correlation. And here, this is T1 crash to functional. So what we have discussed, crash the T1 data to the functional space. And after that, we can do segmentation on the T1 data. So this is the old segment. And usually we're not using that, we use a new segment.tel. So new segment.tel is we will segment the brain tissue into white matter, gray matter, and CSF. So in that way, we have the brain tissue probabilities, and also we have the normalization parameters, because this is a unified segmentation, both have segmentation and normalization. And use those information we can do DATEL. So DATEL is also a pretty good normalization method in SPM. And this is a fun regularization in segmentation. Usually we just use the default European, because each Asian has two field data. And if you use DPARSFA, you have the byproducts of VBRM. So you will automatically have the, for example, the T1 image segment or T1 image new segment folder. You can have this kind of file, the C1 files. So these are gray matter in original space. C2 files are white matter density in original space. C3 files are CSF density in original space. And you can also have the WC1. W means normalization. So this is WC1 is gray matter density in normalized space. And WC2 is white matter density in the normalized space. But you will hear some people call something like gray matter volume. So this MWC1, M means modulated. So a lot of people call the MWC1 as gray matter volume. So you can use these files to do VBM analysis. You have a gray matter density is WC1 and the gray matter volume as MWC1. And you can also do the nuisance queries regression. This is important because fMRI signals are pretty noisy, so we need to remove noise from the signal. So we can do the nuisance queries. And for example, we can do the polynomial trend. This is for the linear trend or the quadratic trend. Usually we just remove the linear trend because from the beginning to the end, maybe there's some drifts. And also, important thing is we need to regress all hand motion. So hand motion, previously people are using rigid body 6, but rigid body 6 nowadays I think not enough, and people are using direct 12, but mostly we are using Friesen 24. So in our paper, we examined all the models and found the Friesen 24 model is pretty good. So we will use the Friesen 24. Although in DPARSFA itself, you can use assay aroma. We will introduce that later. So assay aroma seems recently lots of people like that. And here in DPARSFA, we can use Friesen 24. And this is Voxel 12, but we're not using too much. We're using Friesen 24. And also, you can use hand motion scrubbing regressors. So hand motion scrubbing regressors is you can define the scrubbing settings. So usually we use FD Jacobson because FD power is overestimate. we use FD junction. The threshold, most people are using 0.2, and for scrubbing time points before and after, so long time ago they will use 1 and 2, but nowadays we use FD junction and the threshold is 0.2, and the before and after you just put 0. It's acceptable for the reviewers. So once again, FD junction, threshold 0.2, and 0 before and 0 after, the reviewers accept that. So basically, if you use a Prism 24 and you use a scrubbing, so no reviewers will chasing after you. But also you can try assay aroma. Usually the reviewers will not chasing after you for questions about hand motion. So this is our paper, and this is the ES top 2.1% highly static paper. We're talking about the Prism 24, and you can also use scrubbing. And here is nuisance regressors. So lots of people also talking about wet matter signal, CSF signal regression, and global signal regression. Global signal regression is very controversial. So once we click, we have this kind of queries, and we can use a mask. So you can define white matter mask and a CSF mask. Most times we use an SPM a priori, but you can also use a segmentation. So you have because we did a segmentation, we have a segmentation files, and you can set up a threshold on that. And also you can use a comp call or use a mean. So recently some people propose comp call, so you can set up the number of principal component numbers of comp call. Comp call is basically just merge the white matter mask and the CSF mask and perform principal component analysis. So doing a PCA and select first maybe 5 or maybe more principal components and use that to do regression. But mostly we are using the mean. And also you can do the global signal. So for the global signal regression, you can define the global signal using the SPM a priori or using the auto mask. And basically, because it's so controversial, if you did a global signal regression, hello? If you did global signal regression and some reviewers will ask you, global signal regression causes lots of artifacts, and they will ask you to do the analysis without global signal regression. And if you don't do global signal regression, some reviewers will ask you, global signal can remove lots of noise. They will ask you to do global signal regression. So in our lab, usually we do both with and without global signal regression. So we can have both results, and we hope that can converge. So if you click both with and without GSR, you can have the results without GSR and with GSR at the same time. And here is the other covariates. You can define the other covariates you want to remove, but this is rarely used. If you know what you are doing, you can do that. And this filter. So filter, usually we will put a filter at later, and after spatial normalization and after AFF and AFF calculation. But the parameters set up here will be used here. So whenever you click this button, this will turn blue. So you know this parameter is for this. And this is spatial normalization. So spatial normalization, we should also set up the bounding box and the box size. And there are several different methods to do spatial normalization. So the box size, basically most of the data we acquired is bigger than 3 millimeter box size. We use 3 is okay. But if you want to use 2, usually it just causes lots of spaces, but not too much new information. And this is why we do normalize, because we see the brains, they are very different. So when we compare across subjects and you need to perform some static analysis, then you have to collect them into the standard space. So we have several methods. We can normalize by using EPI templates, or normalize by using T1 image unified segmentation, or normalize by using .tel, or you can normalize by using T1 templates. But this one is hidden on the on the graphical user interface. You can use a code to call that. And mostly used is normalized by using .l. So for the details by using .l is, firstly, the structure image was corrected to the mean function image after motion correction. And then the transformed structure image was then segmented into gray matter, white matter, CSF. And then you will create a .l template. So the good thing for .l is it will create a group-specific template. So every subject is right to the group-specific template, so that makes it better. And then normalize to MRI space. So all the files will normalize to MRI space. Seems pretty complicated, but you do not worry about that because in DPARS, all is done for you under the hook. And this can do smooth. And to smooth, this one thing you need to understand is for regional homogeneity and differentiality, you don't smooth people calculation. Because you know, regional homogeneity is one voxel is coherence with its neighbors. So if you smooth, then there will be a big problem. You inflated the regional homogeneous. So, and this is smooth corner. So the smooth corner can be also applied later in the smooth derivatives. But in most of our cases, we do not smooth before, we smooth after the parameters calculation. And so why to smooth is because we would like to reduce the effects of bad normalization. Because sometimes some people, the normalization effect is not so good. So if you just smooth, you just smooth maybe the bad effects. So it's not too good, but everybody is some kind of bad. So you can align better. And it can also increase SNR because each time series may have some noise. And if you smooth together, the noise will be cancelled. And here is a mask. So when we calculate all the measures, we should be within some mask. And within mask, we can use a default mask. The default mask is SPM, a priori mask, and we structure at 50%. And you can also always define your own mask. For example, you have your own group mask. You just click user define mask and choose your group mask. Then everything will be restricted into that mask. And this is the work mask into individual space. And this function is useful if you want to calculate in original space. If you do not know what it does, you just leave it alone. Because when you set up the templates, you want to calculate in MR space or calculate a regional space, it will set up automatically. And this is detrend. So linear detrend, we have talked about the data may have the linear drifts, for example, so for the homo noise. But usually we will do the polynomial trend 1 in nuisance covariance regression, then we do not need to detrend again. This is nuisance covariance regression. So you can do the nuisance covariance regression at the very beginning in the original space. You can also just alternatively do the nuisance covariance regression after spatial normalization. And but usually we recommend to do nuisance covariance regression at the very beginning. And only if you do the normalization that is normalized by using EPR template. If you use normalize by using EPR template, you have to choose the later nuisance covariance regression. And all the parameters are used, set up here, are used here. So once you click this button, all this will turn blue. So you know those parameters are used here. And this is AR5 and FFF. So in the pre-courses, we have introduced the concepts of AR5 and FFF. So AR5 is basically the amplitude of the frequency band. And for the FFF, it uses the full frequency amplitude to normalize that one. So you will see this normalized one, the signal is stronger. So this is FFF. So you can set up the AFF and FFF here, and it will calculate automatically for you. And then importantly, you can set up the band. So for example, if you read Dr. Xinian Zhuo's paper, so that it talked about some through 4, through 3, through 5 different bands. So you can set up the different bands here, and you can have a different band results. And this, after fMRI calculation, we can filter the time series because people are talking about for function connectivity, we restricted the frequency band from 0.01 to 0.1 because the high frequency, very high frequency band can reflect noise like heart rate, and the very low frequency band may be also noise. So usually we use filter, and the parameters are here, 0.01 to 0.1. And you can, as we said, you can use other frequency bands like through 4 or through 3. Then you can have different answers for different frequency bands. So this is also a hot topic that different frequency bands may have different characteristics. And this is scrubbing. So usually we do scrubbing during the regression, but if you really would like to do the scrubbing at the very end, you can do scrubbing, and you can set up the scrubbing threshold, and you can cut, just delete the time points with high motion peak, or you can just do interpolation, use nearest neighbor, linear, or cubic spline like that. And this is regional homogeneity. So in the pre-courses, we have introduced the concept of regional homogeneity. It's just a voxel with its neighbors. So the conducts coefficient of concordance with its neighbors. So that can indicate the activity strength of a voxel. But usually we know the 3D ray hole has some deficits. Like if this is a gray matter voxel, but this one is a CSF, and that one is a white matter, then it's not functional homogeneity. It's kind of mix of lots of stuff. So when we introduce DPARSFA, then we will know the surface-based regional homogeneity will be better. And this is a smooth record. Usually we do not smooth before, but usually we can smooth all the derivatives at the end. And this is degree-centrality. Degree-centrality is one voxel. Its correlation with all the other voxels in the brain. So this is a graphical method that you can capture the connectivity between one voxel with all the brain voxels. So this is degree centrality. You can calculate that as well. This is Dr. Xinian Zhuo's degree centrality paper. And lots of people are interested in functional connectivity. So functional connectivity in the pre-courses, we also introduced the concept. So for the functional connectivity, we can do voxel-wise state-based correlation analysis. And we can also extract time causes. So for example, if you want to do graphical analysis, then you will need to extract time causes. For example, you use the AL atlases, or you use Dosenbach 160 RIs, or you use maybe like a Schaeffer 400 RIs. You need to use this extract our time courses to extract the time courses. So basically you just click these buttons and it will do automatically for you. What you need to do is define the ROI. So usually here, the mask labels in mask file, that means in the mask file there are several different regions. If you didn't click this one, it will all the non-zero value voxels are the ROI and the zeros are not. But usually you will need to click this one because, for example, the AL file, the different regions have different numbers, and then it can extract all the signals. And the AL atlas, Hubbard atlas, Dosenbach's 160R function RIs, and Angela Hanna DMN RIs, Aqueduct 200 clustering RIs. But most importantly is different other RIs. So in our study, we will read the literature and we have some hypotheses. For example, for emotional tasks or for emotional disease, you think about maybe amygdala has some problem. Then you can define the amygdala as a RI. So define RI, you have several different ways. You can define with a sphere. or you define using a mask. So for example, later we will tell you that in the DPARSFA viewer, we can create a cluster mask. You can use that cluster mask as a mask here. Also, you can add some seed stereos. So for example, at sphere, you read the paper and they will tell you this kind of coordinates, maybe x, y, z, blah, 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 and you can use that x, y, z, define RI. And you have x, y, z, you use a radius, and if you have several RIs, you just use multiple lines. For example, the first line is first RI, second line is second RI. And if the coordinate is terac coordinates, you can just click this one. This will convert terac coordinates to MI coordinates. And this is the default atlases for DPARSFA. It will automatically extract the 10 courses for you. So for example, have the AL atlas, have the Harvard Oxford atlas, has the common product, cross-string RIs, Chomsky 980 postulations, Dosenbach 160, and the global signal, and the Powers neuron 260, and we also have the Sheffer 400 puzzles. So this will be automatically extracted. And you can also do the define RI interactively. So for example, in the later, if you are a neurosurgeon, you are very familiar with the brain structure, you just click some here. I just want to define the RI there. So you need to, I want to define how many RIs and what's the radius, and then you just, it will automatically display the structure file here, and you can just select anywhere you want to define, just click somewhere, and you define, and then click the define RI, and that will interactively define RI. And after function connectivity, you will get the box-wise function connectivity results of each RI, and the working directory results, and FC, and dash some initials, because tell you what kind of preprocessing of that file is. And this Z means Z transformed. So we know the correlation. So Pearson's correlation is from -1 to +1. It's not normally distributed. So we can use Fisher's R to Z transform to transform those correlation values to Z values. So that's much better for the normally distributed. This can be used for t-tests. And RI1 FC map for subject 1, and RI2 FC map for subject 1, like this. And also for RI results, you can also have the RI signals, and you can have the FC signals results. And finally, this is the voxel mirror homotopy connectivity. So in the pre-courses, we talked about it's from the voxel with its symmetric counterpart. And so for prepare for BMC, we need to further register to a symmetric template and calculate BMC, the voxel mirror homotopy connectivity. And firstly, we need to get the T1 image in MI space, and then we get a mean T1 image template, and we just flip it and calculate symmetric T1 template, and everybody normalize to the symmetric template and use that information applied to the function data. So we want to calculate BMC, we need to make sure the brain is as symmetric as possible. And after that, we calculate correlation between one voxel with its counterpart at the other hemisphere, and we have BMC maps. And here is set up parallel workers. So, for example, nowadays, our computer has multiple cores, so we can set up, for example, you have a 4-core computer, you set up 4, then the processing speed will increase by 4 times. This is pretty important later in DPARSFA because DPARSFA is very time consuming. We need to buy some multiple core computer. And this is functional sessions. So for example, you scan the subjects for multiple rounds, and round 1, round 2, round 3. So you can do it automatically in DPARSFA. You just, the first session is fun roll, the second session is S2 fun roll, and the third session is S3 fun roll. and then it will automatically process all the rounds for you. And this is the final starting direct name. So after you set up all the parameters, you set up the starting direct name. So that means DPARS can start from any step. So for example, you process the data and you do not want from the beginning to do something. You can just, okay, after the spatial normalization, and I want to continue to filtering and then do function connectivity, and you can just start with those after spatial normalization and check off all the previous check boxes, and just starting from there to the following studies. And it will tell you different starting direct name means what. For example, fine image ARW, A means search timing, R means real line, W means spatial normalized. If you click, you have the abbreviation. A is search timing, R is real line, W is normalized, S is smooth, D is dechain, F is filter, C is covariant removed, B is scrubbing. And some other calculations say what, but this is no longer maintained. And what we have discussed is preprocess in fMRI space. And you can also calculate in original space. Just in the temporal parameters, you select calculating original space. And the difference is the normalization is no longer at the beginning, but at the end. And these parameters will be also used as normalized derivatives. And smooth derivative at the end. And here, use this kind of parameters. And the warp mask into individual space is, if you calculate it in original space, you need a warp mask into individual space. So this will be automatically checked for you. And then this is intraoperative processing. For intraoperative processing, everything should be quick. So they skip the real line because the subject is under anesthesia. And you can define the RI interactively and just very quick to see, okay, if there's tumor, so on the healthy part, you just click RI and see how the functionality displays in the tumor. And you can also do VBM. VBM is a byproduct. If you do not have function data, you just want to do VBM, you select VBM, and this new segment data was checked, and you can set starting directly at T1 row. And then this blank is also important. So sometimes I just want to perform one step in the processing, and there are so many checkboxes. I do not want to check off one by one. You can select blank. After you select blank, all is checked off, and what you need to do is just check the single step you want to do. And this is blank, everything is checked off. And you can click the save to save the parameters to .mat file. So that means all the settings are saved in the .mat file. So the .mat file, later you can check every settings, and you can even load up the private setting ups. If you forgot to manually save the parameters, every time DPARS runs, it will automatically save the parameters .mat for you. So later you will check that, and you can load parameters. And we have put all the courses online. You can visit up.course, and up.course we have both English versions and Chinese versions. You can go to see whichever you want to read all the courses, how to use DPARS, how to use DPARS, how to use DPARS. And we also wiki, and we also have the journal club. Every Friday morning, we will discuss literature in fMRI field. And if you want to join, you can go to online streaming. And you can also follow our official account of Live. And also, because this is our workshop, this is training shop in English, and we do not have a hands-on session. If you really need a hands-on session to solve all the errors you encountered, you can go to, in this October, we have a hands-on training session. And this will be continuing you can just look at AppleDog to look at what the next on-site hands-on training session is. You can join on that. And also, this is just some follow-up training. And this is one thing is DPARSFA is very computational intensive. So we know for the surface reconstruction, one subject, one core can be 1 day. So it's important that we have multiple core computers. For example, if you only have one core, then if you have 100 subjects, you need 100 days. And we do have some not too expensive solution. So for the DPIB computational core, it can have a parallel computing, and per day it can process 20 subjects. So if you're interested, you can visit deepbrain.com DPAB core, and that can process about 20 subjects a day. So, and this is the WeChat official account of our lab. If you're interested, you can just scan and follow the WeChat account. We will announce the news and the latest journal club will be. And thank you very much. This is my life, and thank you much for your listening. And